Right, let's get straight into it. If you've ever stared down a complex algebra question on your Cambridge paper and felt that instant wave of panic, listen up. You are definitely not alone. Today, we're building a bulletproof strategy to conquer a topic that terrifies a lot of students, logarithms. But here's the secret. It's just a tool. And by the end of this explainer, we're going to turn this intimidating mathematical concept into your ultimate advantage in the exam room. We are drawing directly from the 0580 syllabus. No fluff, just the exact evidence you need. Let's dive in. Okay, here's our flight path for today. 1. Understanding inverse functions. 2. Introducing the logarithm. 3. Translating base and index. 4. The rules of logarithms. And finally, 5. Solving exponential equations. Let's get to work.
Section 1. Understanding inverse functions. Reversing the effects.
So, to truly master logarithms, we actually need to rewind for a second and look at inverse functions. Think of an inverse function like a mathematical undo button. Its entire job is to reverse whatever the original function just did. If the function walks you 10 steps forward, the inverse walks you 10 steps back to exactly where you started. The Cambridge syllabus is super clear on this, giving us a foolproof 3-step mechanical process. First, you write the equation out in terms of y. Second, you literally swap the x and y variables right there in the equation. And third, you just use your standard algebra skills to rearrange the whole thing and make y the subject again.
It's beautifully simple in practice. Look at this. If our original function is y equals x plus 2, the inverse, after you swap and rearrange, is just y equals x minus 2. Makes sense, right? Addition is cleanly reversed by subtraction. Multiplication gets undone by division. But what happens when the equation isn't just basic arithmetic? Section 2. Introducing the logarithm, the undo button for powers. Before we continue, I want you to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so we know how to reverse a simple x plus 2, but we hit a massive wall when our unknown variable isn't just sitting nicely on the ground floor of our equation. What if it's trapped way up in the exponent? Look at this problem. If 2 to the power of x equals 32, well, we can easily guess that x is 5, right? Because 2 times itself 5 times gets us 32. But what about 3 to the power of x equals 12? We know 3 squared is 9, and 3 cubed is 27. So x has to be this messy, horrible decimal floating somewhere between 2 and 3. How on earth do we actually extract that exact x value in an exam? Enter the logarithm. This is your ultimate undo button for exponents. By definition, the logarithm of a number is literally just the inverse of the exponential of that number. So, when you see log base a of y equals x, it's telling you the exact same mathematical story as a to the power of x equals y. It's simply the mechanism we use to drag that exponent down onto the main line where we can actually do math with it. Section 3. Translating base and index, speaking logarithm. Here's the thing you need to realize. Logarithms aren't some weird alien form of math. They're just a translation. It's like saying the exact same sentence, but in a different language entirely. We're translating the index notation we already know into logarithmic notation. And you've actually got this translation tool sitting on your desk right now. Look at your scientific calculator. You'll see that standard log button. Now, as our source points out, if you press that button without telling it a base, the calculator just assumes you mean base 10. So if you type in log 100, you're basically asking your calculator, hey, 10 to what power gives me 100? And the calculator spits out the answer, 2.
And this slide brilliantly illustrates that direct equivalence we just talked about. On the left side, speaking in index notation, we say, base 2 raised to the power of 5 equals 32. Over on the right, speaking logarithm, we say, the log, base 2, of 32 is 5. Notice how the base stays exactly the same in both. The logarithm is just specifically isolating that exponent. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, back to the math. Because of this direct translation, we get 3 absolutely crucial shortcuts. You need to memorize these for your exam, seriously. First, log base a of a is always 1, because anything to the power of 1 is just itself. Second, log base a of 1 is always 0. Why? Because anything to the power of 0 is 1. And third, log base a of 1 over a is always -1. Spotting these instantly will save you massive amounts of time on the paper. Section 4. The rules of logarithms, wielding the tool. Okay, now we know what they are, let's learn how to use them to build our case. Since a logarithm is fundamentally an index, a power, it has to play by the rules of indices. These operational rules are what let us take big, clunky algebraic expressions and simplify them down. Look at how cleanly these work. The addition rule? It says that adding two logs with the same base is identically equal to multiplying their contents. So log 5 plus log 3 just collapses into log 15. The subtraction rule means you divide the contents. So log 12 minus log 4 becomes log 3. But here is the real game changer, the power rule. It lets you take an exponent that's stuck inside the log and literally pull it right out to the front as a multiplier. That right there is your secret weapon. Section 5. Solving exponential equations. Real-world application. So, why go to all the effort of memorizing these rules? Because they give us the undeniable evidence we need to solve exponential equations that would otherwise be literally impossible to do manually. Let's apply this to that messy problem from earlier. 3 to the power of x equals 12. Step 1, we take the base 10 log of both sides. Step 2, we deploy that amazing power rule we just talked about, which lets us pull the x down in front. Now we have x times log 3 equals log 12. Step 3, basic algebra, just divide both sides by log 3. Step 4, punch that into your calculator, and boom, we get our precise answer. X equals 2.26. We've successfully unlocked the exponent. Now, I hear this all the time, the classic student objection. When will I ever actually use this in real life? Well, the Cambridge syllabus points us directly to one of the most vital financial concepts you will ever deal with: compound interest. Let's set the scene. Imagine you deposit $1,200 into a savings account that gives you a 4% compound interest rate every year. How do we build a mathematical equation to express the total amount, let's call it S, after an unknown number of years, T? If you're trying to figure out exactly how long it takes for your investment to double, you are hunting for a variable that is trapped in time, an exponent. The absolutely crucial step here is setting up your multiplier correctly. A 4% increase means you keep 100% of your original money and you add 4% to it. That's 104%, or 1.04 as a decimal. So your total sum S is going to equal your starting amount of $1,200 times 1.04 to the power of T. See that? That T, the time in years, is our exponent. Let's look at the concrete evidence of exponential growth. In year 0, you've got your $1,200. After year 1, it's $1,248. By year 3, literally without lifting a finger, you're sitting at almost $1,350. The growth accelerates over time because you are earning interest on top of your interest. Now, if you wanted to calculate exactly when you'd hit $5,000, you just set S to 5,000 and use your logarithm rules to isolate and solve for T. It's incredibly powerful. And honestly, that is the true beauty of logarithms. They let us take systems that grow exponentially out of control, like compound interest or population growth or radioactive decay, and give us the mathematical tools to flatten them out. Pull those variables down to earth and calculate exact, precise answers. By turning exponential growth into basic multiplication, what other complex systems in our world could logarithms help you decode? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. I'll see you in the next one.